Okay, so again, at a high level overview, we saw so far only a single linked list based implementation, and I said we will treat the data node next to the head node as the top of the stack. Accordingly, then the last data node in the single linked list will become the bottom of the stack. And we saw that we cannot do it the other way, means we cannot use the last data node as the top of the stack. In that case, you will see how difficult it will be to do the push and pop operation in terms of time complexity. In terms of that, it will be like state of n, you have to go through the entire linked list to push or pop. Instead, if we do like this, we can accomplish the push and pop in state of one time without going through a loop. Now, in the case of a double linked list, since we can traverse in both directions, we can use the same logic that we had in the single linked list. Treat the first data node to correspond to be the top of the stack and the last data node to be the bottom of the stack. We can do that. And since we saw that already how to do that with the single linked list, we'll do it the other way, that we'll treat the last data node as the top of the stack, and which can be accessed right away using the tail node. So like we access the first data node from the head node, you can access the last data node in the forward direction from it is the last data node in the forward direction, but it is the first data node in the reverse direction. So from the tail node, we can access this data node in constant time. We don't need to go through a loop to access this data node. So that's what we'll be using. So we'll use the data node that is the previous node to the tail node. So this data node is the previous node to the tail node, and we'll treat that as the top of the stack. And this node will be then becoming the bottom of the stack. The first data node in the forward direction will be the last data node in the reverse direction. So that will become the bottom of the stack. Okay. So again, we saw a double linked list at a high level overview last class. So this is how it will look like. So we have in each node 3 member variables. The data member variable that you want to store, in this case we'll work with integers, and then the previous node pointer and next node pointer. So the previous node pointer will store the address of the previous data node, and the next node pointer will store the address of the next data node, okay, the following data node in that direction. So from the head node, we can reach this node. So we need the address of the next data node to the head node, which is 200. So that's what is stored in the next node pointer. From this data node, we can reach this node at address 500. So the next node pointer will be 500. And then from here, we can reach this node at address 300. So the next node pointer is 300. And then this is the last data node in the forward direction. There's no data node following this node. So the next node pointer is set to null. So you should not be storing the address of the tail node in this data node. There's no need for that. Okay. So again, the head node and the tail node are dummy nodes. So you should not be storing any data and unnecessary pointer values in those nodes. Alright, so from the tail node, so the head pointer stores the address of the head node, and from which you can traverse in the forward direction. Similarly, the tail pointer will store the address of the tail node. So in the node class, each node has these 3 member variables. So in the the stack class, which is similar to the list class before, you're implementing a stack as a double linked list. You'll have the head pointer and tail pointer. So these are the 2 member variables for a double linked list based implementation of a stack. So the head pointer stores the address of the head node, which is in this case 100, and tail pointer will store this address 400. So then using the tail pointer, you can access the tail node, and the tail node will have the previous node pointer set up. So we'll not set up the data and next node pointer. We'll assign a value only with the previous node pointer. So it's okay to have the other 2 member variables to be just left as it is. So using this previous node pointer, we can access now this data node at address 300. And the previous node pointer here will have the address of the previous data node, which is 500. And you can access this node. And using this previous node pointer value at this data node, you can access this data node. And this is the last data node in the reverse direction, starting from the tail node. So there's no data node previous to this node. So the previous node pointer should be set to null, not the address of the head node. Okay, so you should not make the mistake of storing the address of the head node. So now we'll follow the convention of using the last data node. So when I say always last data node, that means in the forward direction, right? So that also means the node previous to the tail node as the top of the stack. So if you want to represent these three integers as a stack, you should be writing the 5 at the top of the stack according to our convention, and then the 10 will become the bottom of the stack. So this is the stack we are going to create. Okay. So the function, the class for the node here, again, as I said, we'll have 3 member variables: the data, next node pointer, previous node pointer, and you have the set and get functions. We saw this also in previous class. Now in there we saw the list AD class list, and we saw this stuff. So as I showed you for single linked list based implementation, you rename this as class stack, and this is constructor should then be called stack. So you're creating the 2 dummy nodes, the head node and tail node. So that's what this code is accomplishing. The head node is created here. When I say new node, and you store the address of that in head pointer, and then you create the tail node and you store the address of that in the tail pointer. So the 2 nodes are just set up. The head pointer stores the address of the head node, and the tail pointer stores the address of the tail node. The stack is initially empty. We are just creating a stack. So we have not yet pushed any data to it. So we need to initialize the next node pointer in the head node to be null. So that's what I am doing here. Head pointer arrow set next node pointer is set to null. So that means the stack is empty. So from the head node, you cannot reach really any data node. The next node pointer in the head node is null. Similarly, the previous node pointer in the tail node should be set to null. After you push, you will have some non-null value, but initially when you create the stack, this should be null. So it's also the previous node pointer for the tail node should be set to null. So as you can see, these are the things that you want to initialize. You don't want to initialize the previous node pointer for the head node or the next node pointer for the tail node. There's no need to set values for them. So that's how you create a stack. And then you have the get functions that will get you the value of the head pointer and tail pointer, which will be the addresses of the head node and tail node. Now to check if the stack is empty, you see you have an option here. You can check if the next node pointer for the head node is null. That's what we did for a single linked list. If it is null, we can say the stack is empty. We can do that. That's what I have done here. If the next node pointer for the head node, if it is null, then you can return true, the stack is empty. Now if this is true, if the next node pointer for the head node is null, then automatically the previous node pointer for the tail node should also be null. So instead of this, we can say if tail pointer arrow get previous node pointer is null, then you can return true, otherwise return false. So that's another way to implement the isEmpty function for a double linked list based implementation. So either one should be fine. There's no need to check both. If one is true, the other should also be true. Okay. Is that clear so far for a double linked list based implementation? Any question? Okay, so you have time to focus on the push operation. So let us, again, this is something important to understand. Make sure you understand this. Let me make sure I'm recording this. Okay. Okay, so let us see how to push to the stack, which is in this case a double linked list. So you want to be able to add something here near the tail node. Okay, so let us use this code and go through an example or kind of figure this figure accordingly. Okay. All right. So we'll call this push function, and you pass the data that you want to add to the stack. So again, we want to do this in constant time. So we'll see that there's no looping involved here. So we'll set the new node that you want to create. Okay. because it anyway create that node and set the data for that node. So create the new node and make the new node pointer to store the address of the new node, and you set the data for that new node. Okay, now let's see if you have an example. So I have set up the new node. Let me copy one node here. Okay, so let us say this is my new node, created at some address, say some 800, and I have currently set up its data, and the new node pointer is going to store that address, and it's going to point to that node. So that's what these two or these three statements is going to do, or these two statements. The new node is set up, and the new node pointer is going to store the address of that node, and you set up the data to whatever the data you want to add to that stack. So let us say I want to add some other value, say 10, or 10 is already there. Let us say it is some 7. What is not there? 1095. Okay, I'm adding always something that is there. Okay, let's say 8. Alright, so that's what we do with the two statements. Now the third statement, new node pointer arrow set next node pointer is set to null. Now think about this. So we are going to insert this as the node just before the tail node. So that means it should look like this node, right? So this is the top of the stack, and that's the node previous to the tail node. So as I said, this is the last data node in the forward direction. So its next node pointer has to be null, right? That's last data node in the forward direction, and the first data node in the reverse direction, the node previous to tail node. So for that node, the next node pointer should be null. So we can right away set the next node pointer for this new node that we are going to insert. Still it's isolated. Okay, I'm going to the code statement by statement. So this is what we have so far. We set up the node, make the new node pointer to store that address, and now we can set right away the next node pointer to be null for that data node. Okay, because it's going to eventually become the node previous to the tail node, and for such a node the next node pointer value should be null. Okay. Now what else we have here? Now I'm going to getting into my double linked list. I access the tail node using a tail pointer. So tail pointer arrow get previous node pointer. So I'm trying to get the address of the node previous to the tail node that is currently in the stack. Okay. So and I store that address in last node pointer. So let us assume this is the stack that we currently have. Okay, so I should have done this before the class, but let me do that. I'll clear this up after the class and add a separate slide, but let me just do this quickly to show things. If it's in a classroom, I could have just done this in a board, but okay. Alright, so what you are doing right now is this. So the top of the stack is currently this, right? That's the last data node. So with this code, the last node pointer is going to store the that last data node address. So how we get that? Using the tail pointer, access a tail node, arrow get previous node pointer. So I am getting this address 300. That's the previous node pointer value in the tail node, and the last node pointer will store that value 300. Okay, so that's what we have so far. So now we are going to check if this last node pointer, that's the address that we used, that the address of the node previous to a tail node, we check if it is null. Now think about it. When would the last node pointer, based on these four statements, which is really this last statement that is setting the last node pointer, when would that be really null? It would be null if the value stored in the previous node pointer for the tail node is null. So if this value is null, then last node pointer will be null, right? Because we are storing only this value, the previous node pointer for the tail node, in the last node pointer with this statement. So when would this previous node pointer in the tail node be null? If the stack is empty to begin with, there's no previous node to the tail node. So if last node pointer is null, that is one scenario that when we are doing the push operation, there's no other node in the stack. That means the stack is currently empty and you are pushing that data to an empty stack. So that is one scenario that we have to deal with. If the last node pointer is not null, that's a different scenario. That means the stack has at least one element already there, and we are pushing that new data to the top of that stack that we currently have. So these are the two scenarios we have to handle, and that's what I have shown here as a separate slide, the two scenarios. Okay, and okay, I have a slide here that shows these operations. Okay, I do have something now here. Okay, so this statement here, 1, is shown here. The new nodes, next node pointer set to null, right? And let us see now, the last node pointer, it's not null, right? So in this example we have is 300, so it's not null. So this corresponds to scenario 2. Alright, so let us see the code for that. So if the last node pointer is not null, what we really want to accomplish? We don't want this node to be really the last data node, right? We want this, our new node, to be the last data node. So we want to accomplish that. And not only that, we need to link this new node to this linked list, right? So we need to take care of those things. Let us see how to do that. So the last node pointers, next node pointer. So right now this is the last data node. So its next node pointer was set to null. That should no longer be the case, because this is not going to be the last data node anymore. Our new node is going to be the last data node now. So we need to change the next node pointer value. Instead of 0, it should store the address of this new data node that we created. So how we can accomplish that? Access the last node using the last node pointer. So last node pointer, arrow set the next node pointer to be this new node pointer 800. And that's what this statement is doing. So you should try to understand the code like this using a figure. Last node pointer, arrow set next node pointer to be the new node pointer. So that will be this 800. Okay, so that means we have now set up the link from this last node to this new node. Then the new node's pointer, previous node pointer, should be the last node pointer. So right now this previous node pointer for the new node is not set up. So remember, this is a double linked list. So we have to set up the links in both directions. So this will set up the link in the forward direction. Now we have to set up the link in the reverse direction. So how we do that? The new node's previous node pointer should be set to be the value of the address of this last node. So that should be this 300. So when you set the previous node pointer value for the new node to be the address of the node that's currently the last data node, you're setting up the link in this reverse direction also. So that's what I've shown here in general with these two statements, number 4 and 5. You're setting the link from the last node to the new node and the link from this new node to the last node in both directions. And then you come out of the else block, and then what you have to do, we have not yet set up what? We have to break this link. Still, the tail node's previous node is this node, the last data node, this one, that's pointer by last node pointer. But this is no longer the last data node. The last data node should be this new node that we just created. So how can we accomplish that? So instead of 300, we should store this 800 as the previous node pointer value for the tail node. So how we do that? The tail pointer arrow set previous node pointer and pass the new node pointer as the argument. And that's what we are doing here. Tail pointer arrow set previous node pointer and new node pointer. That's going to create the link like this. So this will be now this 800, and that way you are pointing from this node to this node. And that's what I've shown here. From the tail node, now you can access the new node and not anymore the last data node. So this new node now becomes the last data node, and that's the push operation. Any questions so far? Okay, so let us take a couple of more minutes to finish off this. Now, this is if the last node pointer is not null. If the last node pointer is null, that is really like pushing to an empty stack. So pushing to an empty stack means the stack is currently like this. So what we have to just set up is create the new node like I just shown here, and then do what? You can set, so these statements that you had earlier before the if block will still be applicable. We have to just do these two things. What are those two things? The head node's next node, which is currently null, should be set up to the address of this new node. So how we can do that? Head pointer arrow set next node pointer to be the new node pointer. So the head node's new node, the head node's next node pointer should be set to this 800. So when we do that, we can access from the head node to this new node. And this is also the only data node. The stack is currently empty. So that means this node should also become the node previous to the tail node. So how can you accomplish that? The tail node's previous node pointer should be set up to the address of this node. So the tail pointer arrow set previous node pointer should be to this node. Now one more thing needs to be done. What is that? This previous node pointer field in the new node is not yet set up, and we know the stack is currently empty. So that means this is also going to be the last data node in the reverse direction. There's no node previous to this node. So that means this should be set up to 0. If this is the only data node that's going to be the stack, its next node pointer should be null as well as the previous node pointer should be null. And these are three things that we will do right now. So if the last node pointer is null, that means there's no node currently previous to the tail node, which means the stack is empty. That means the head node's next node pointer should be set to the new node pointer. Okay, that means you're creating the link in the forward direction from the head node to this node. Then I am setting the new node's previous node pointer to be null. I am setting this to be null. And then you come out of the if block and set up this link from the tail node to this node. The tail pointer arrow set previous node pointer to be the new node pointer. So you see this statement is common to both the scenarios, because you have to anyway link from the tail node to the new data node, irrespective of whether the stack is empty or not empty to begin with. So that's why I put this statement outside the if block. If you want to put it inside the if else, you have to put it in two places, once here and once here, the same thing. So instead of putting the same thing in a couple of places, I just put it outside the if else, or after the if else. I'm setting the tail node's previous node pointer to be the new node, and you have to do that in either way, as we saw earlier too. So that's why I have it outside the if else. Right, so this is how you accomplish a push operation without going through a loop, just inserting at the tail end of the double linked list. Okay, So go through this code. You can ask me any questions if you have in the next class, and we'll then focus on the pop operation. Alright? Any questions quickly? So it's quite easy. So draw it out like this, and that should be easy to understand. So that